Greetings. In this quick one, I will list the isomorphisms of a C-free cycle graph. So this is basically an example of working with isomorphisms in graph theory. So if we have a cycle graph, C-free, what it means is we have three vertices in this cyclic manner, and I'll name them 1, 2, 3, very usual notation of naming. And I'll quickly introduce what it means when there is an isomorphism in graphs. So 1, 2, 3, 1, 2, 3. So in graph theory, when we talk about the isomorphism, and let's say that C3 will be some G, and then we have some graph isomorphic to it that will be called H. So we're looking for, in a second, I'll be listing all the possible graphs H that are isomorphic to this graph G. So if I have an isomorphism with graphs, what I have is some function, I just call it F, some function that creates a bijection. Isomorphism is a bijective homomorphism, meaning we have this relation between same order sets of same number of elements, so that we can have one-on-one correspond-to-one correspondence between all the two different elements for those two respective sets. Okay, so we have a function f, which is a mapping from the vertex set of one of the graphs to the vertex set of the other of the graphs. Now, because it's bijective, we can also switch it, but I'm just working with this order now. So we have isomorphism from G to H in the way that from the vertex set of G to the vertex set of H, so that G and H are thereby isomorphic. So we see that the basis here is, there's one more property I'll mention in a second, very important one. The basis is that we have the same number of vertices. And then a lot of time, we just rename the vertices, move them around, and that creates the isomorphic effect. So that's what changes the graph. And it can change the graph quite drastically or not that drastically in the case of a cycle. What we'll see here, what I'll be showing here when I'm listing the isomorphism for this one in a second. And there's one more thing. If we have some UV that are in the vertex set of G, and then we have H UV in the H set of G in one of the graphs, that can be only if we also have f of u, which is a new vertex u under the isomorphism function f of v, mu v under the isomorphism of f. That means basically the placeholder for what u or v respectively were in v within the vertices of v, now in H. So we apply f to the u, f to the v, f to the vertices in order to make it the vertex inside the H. So now it's a new H, f of u, f of v instead of uv. That will be in the surprisingly H set of H. So we transform the vertices so that we preserve edges. So isomorphism in graphs is this bijection from the vertex set of one graph to the vertex set of another graph, so that we are preserving edges, so that we are making sure that when there was an edge, it will be kept, even when the vertices are seemingly moved around. The bijection creates such relations such that the edges are preserved as they were. Okay. So now let's look for all the possible isomorphisms of a C3 cycle graph. Now, for cycle graph, Cn for n higher than 2, because n equals 2, you cannot really have a cycle. The idea of a cycle graph, it goes in a cycle. If you have only 2 vertices, yes, I can make an isomorphism, by the way, for it. I already said that in isomorphisms, this is a simple graph. We're not specifying the direction of it H anyway, so an isomorphism is not really required if I rename the vertices like this. I would now say that this is, for example, a possible G, this is a possible H for this pattern. I'm just not saying that this G is no longer what we're talking really about here mainly, but side example, I'm going to delete it in a second. But let's consider, it's basically a path graph, like a straight line with vertices in it. Because it doesn't have two edges between the same vertices, I'm working with simple graphs. No loop anywhere also, although that wouldn't really help. So the cycle is not there really. So for n equals 2, it's not really a cycle in the usual sense one would expect. So that's why we're talking about C3. Then C4, C5 have far more isomorphisms. If I'm listing them all, C3 is a good choice because we don't have to list too many, won't take a lot of space on while listing it and time to list it. So we have this one. Now let's look for the isomorphisms. Now, for cycle graphs, there's this property. If they have n vertices, they have 2n isomorphisms. And how are these 2n isomorphisms created? First of all, one of the isomorphisms is the initial graph itself, and then we have 7 more. How are those 5 more in this case? In this case, because there's 3, so there must be 6, right? So there's one of these, and then 2n minus 1 more. 5 more in this case. Made by rotations and reflections. Reflection means I can like draw a line through, for example, 1, then I reflect it about that line. That means I switch the 3 and 2, or I switch the 1 and 2 in the graph, and then I rewrite the graph. I just draw the same graph, and I just switch the names for these 2 vertices. Just switch these 2, switch these 2. And rotations are, I just move each of them, for example, I do clockwise. So 1, 2, 3, that's the new setup. One more time, and the third time I'm back at this initial position. So I can list it. So I'm now going to be listing all the possible isomorphism we have solved for C3. So for Cn, we have 2n isomorphisms. Alright? I'm not going to write isomorphisms, but that's that. So for Cn, we have 2n isomorphisms. So to rotate it, we have 2 rotations until the third time we will get back. So we have 1, 2, 3. That's 1, and another one. Again, as you see, I'm preserving the same shape. There's nothing gonna change with these cycle ones. 1, 2, 3. Just replacing the vertices by different ones in the same graph, moving them around. So these are 3 things we have so far. 2 new isomorphisms. These 2 are a possible H that will be isomorphic to the initial G. This is the initial G. And now we have 3 more options. We will switch 2 of these, 2 of these, 2 of these. So I'll switch 1 and 2 first. So again, I'll draw the 3 remaining possible isomorphisms. As I said already before, we knew there were going to be 2n for Cn. So we have 6, and that's what it ended up. So we have 2, 1 here, 3 stays. We can switch 2, 3, so I'll do 3, 2, and the 1 stays. And we can also switch 3, 1, so it will be 3, 1, and the 2 stays. So these are 6 isomorphisms according to the Cn has 2n isomorphisms. So this happens with namely cycle graphs, 2 and higher. It would also happen for 4, so we would have 8 of them. For C5, we would have 5 of them. C4, by the way, for example, or C5. C5, for example, looks like it's again like a regular thing. We have 1, 2, 3, 4, 5, right? That's the idea. C10. But those would have far more, so we would have to list more. And one more thing to mention before wrapping it up. The cycle graphs, their isomorphisms, are equal to the number of the elements of a dihedral group, Dn, or also denoted D2n in abstract algebra. Because there's not some basics about graphs, like vertices and edges, is required knowledge to understand this, definitely. But abstract algebra are not necessarily needed to interconnect, although isomorphism, homomorphism are already things that are very widely used there. So, related concepts. But there is a reason why there's 2n of them, and it's because when you have the list of the symmetries of regular n vertex set shape, and you're looking at it from the geometrical standpoint, right? Now we have a triangle basically geometrically, or we will have a square, or a pentagon, hexagon, and so on. With those shapes, we have 2n vertices and 2n of those symmetrical symmetries. And the dihedral group lists these symmetries as functions, as basically a subset of, if we have, in this case, by the way, if we have 1, 2, 3 as a set of vertices, we can also view it as the different permutations of the 3 numbers in a row. So if you have 1, 2, 3, you can also write 1, 3, 2, 3, 2, 1, and there's always n factorial options. for 3 factorial is the same like 2n. So in this case, the dihedral group is equal to some so-called permutation group. But in other cases, it wouldn't be. I don't want to slide too much in this direction because it's a lot to take into account in case one would be looking deeper into that. But let's just say that if I have in abstract algebra, I'm just going to do a quick side note. If we have some, let's say for 1, 2, 3, it's a little bit of an exception, but it doesn't affect the validity of what we've done here anyway. At 1, 2, 3, 4, 5, we have 5 numbers. It doesn't matter that these are closer, just I'll write it once again not to be confusing, for this not to be confusing in any way. And then 1, 2, 3, 4, 5, and then first option is the second row. We just said we're talking about the set, ordered set 1, 2, 3, 4, 5, and then here we have this 1, 2, 3, 4, 5 repeated. But the way that we can deal with this is we can list all the different orders while always repeating the same row in the normal order, and the second row we can do any order of these 5 numbers. So the number of these options is how many numbers there are factorial. So in this case 5 factorial different options. So I could do 1 and just switch 2 of them. But you see there's already a small change, but the way, how many changes we can make is in this case 5 factorial. And 5 factorial won't be equal to 2n. But in this case, we had 3, we had 1, 2, 3, and slightly related to it was the way that we were reorganizing the vertices here. We would have 3 factorial according to this permutation idea. But that's not always equal to 2n. So n factorial is not equal to n, because 3 factorial is 3 times 2 times 1, that's 6, that's equal to 3 times 2, 2n in this case. But for 4 and higher, we would already, in the context of abstract algebra, where we would have a permutation group and dihedral group. Dihedral group doesn't always, for higher numbers, doesn't have all the elements that the permutation group would have. So when we look at all the options in which we can change the order of particular amount of number or different numbers, there's for higher than 3, we will have more of these options than symmetries when we refer back to the geometrical standpoint of how many vertices our shape, whose symmetries we're looking at has. But not to slide too much in that, if that wasn't understood, it's not necessary. The main point, to reiterate here, now we're getting to the end, let's, one last time, let's review what we've done. We talk about the example isomorphism of a cycle graph, C3, of 3 vertices. We've listed all the isomorphisms. 2 of them, 2 isomorphic graphs, these, namely H, are created by rotating it, and 3 are created by changing taking the 2 adjacent vertices and switching them. And now it's a bijection because we can also write it in a formal way. I could say we have a bijection such that from 1, 2, 3, if I do in this case 1, 2, 3, that was the initial order. I changed into an order of, for example, 3, 1, 2. So 3, 1, 2 was the same positions, that position 1, 2, 3, that's initially 1, 2, 3, now had numbers 3, 3, 1, 2. And so that would now link me to the change. So that would be the bijective function basically telling me how the vertices changed. And turns out that that's what I can use in order to see that the edges were preserved. If I do this function for the u and v, I will basically find the respective u and v according to which of these options I choose, and I should be able to look for the corresponding edge, that it was kept. Because if you reorganize numbers like this, you would expect the edges to kind of disappear, especially more complicated graphs. But the isomorphism takes care of that.